Today we're going to start Chapter 10's second part, which is going to start with Hess's Law in Section 10.7. So I want to give you kind of a practical thought through what Hess's Law is all about. Hess's Law says that if I go from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction is in one step or in a series of steps. So I want to take a look at our bridge situation here. I'm going to pick up the red. So what it's basically saying is, let's say that I can walk from point A to point B to this bridge. And from point B to point C, I can walk. And from point C to point D, I can walk. What I want to know is the amount of energy it's going to take me to walk from point A all the way across to point D. Okay, so Hess's Law says I can figure this out without doing it if I already know some other information. So if I know the distance from the amount of energy that it takes to walk the distance from point A to point B, and I happen to know the energy that it takes to go from point B to point C, and I know how much energy it takes to go the distance from point C to point D, that I can add all three of those up and come up with the total distance. And then this is a really, really simplified form. It has nothing to do with Hess's Law as far as how we do the problems, but it's just something I thought maybe you could visualize it and it would make a little bit more sense when we get ready to do these. What would be the purpose? Because some reactions are just not feasible to carry out in the lab. So going straight from point A to point D is just not feasible. However, if I can go from point A to point B, and then from point B to C, and then C to D, and add the energy it takes to get all the way across there, I'll know how much energy it would take to go through that, to run that reaction. So here's an example of a reaction, and it is an endothermic reaction because it's going to take in 68 kilojoules to do. And it says this reaction can also be carried out in two distinct steps with enthalpy changes, and we designate those by the H2 and H3 that we're going to see here. So this is saying that I can take these two reactions and add them together in a way so that I can get this final reaction, this original one up here actually that we want to, it's this final one down here, and that I can take the delta H of each of those reactions and add them together and come up with the amount of heat that's needed to either be absorbed or that will be given off by the reaction. And that's how they get the 68 kilojoules. And this process is one we're going to go through and show examples of, so I don't want you just to wig out and think that you should automatically know how to do this. But what they've done here is they've said, okay, I know I need N2 as a reactant and O2 as a reactant, and I need NO2 as a product. And that gives us NO on one side and NO on the other side of the arrows that we can actually cancel out because they're on both sides as a reactant and as a product. And that a number of moles of the same type of compound or molecule, this is oxygen in this case, in gaseous form, the state also has to be the same, is additive. And then we can just add those two together and get the 68 kilojoules. And we're going to do examples, and these are the types of problems that you're going to have for homework. And one of the things you need to keep in mind is that it's a problem-solving process. So if you don't succeed the first time you try it through and your paper gets really messy, stop and try again. It may take you a little bit to get the hang of it, but it's not a difficult process, and it's kind of fun to do these types of problems. All right, a couple things to keep in mind, and we covered this while you were doing your homework assignment today in class. It says if a reaction is reversed, the sign of the delta H is also reversed. So we found that. You reverse the reaction and reverse the sign. And the magnitude of it is directly proportional to the quantities of the reactants and products. So if the coefficients are multiplied by an integer or we divide them through by 2, then we do the same thing to delta H. We're going to take a look at a problem. We're going to consider this following data. Here's the information that we have. 2 separate reactions, 2 separate delta H's. And what we want is to calculate the delta H for this reaction. So this actually is our answer, and our delta H is our final answer. So this is what we want to come up with. Okay, so I've rearranged our problem, and if you look up here at the top, that's where we have the reaction we want to come up with, and this is what we have here to look at. So we're going to talk about the left and right side of the arrow. So on the left side is your reactants, of course, and the right side is your products. So we need to make sure that we have the correct reactants on the side of the reactants and the products on the side of the products. So if I look here at my reactants, which are NH3, H2, and O2, you'll notice that none of those are reactants. However, the product here, N2 and H2O, those are the products that need to become reactants. So to do that, what I'm going to do is I'm going to flip the reactions. So when I flip the reactions, I'm also going to flip the sign on the delta H. So this is where it can get a little messy. We're going to go ahead and flip this reaction and make our products reactants and vice versa. And make sure that you write down the state of the reactants and products too, because you can't cancel things or combine things that are in different states. So these are all gaseous, so we're okay with that. So just write this and reverse it. Here's our NH3, which is going to cause us to change delta H to negative 46 kilojoules. All right, so I no longer need this reaction, so I usually just do this to mine so I don't get confused. Okay, I'm going to also have to flip this reaction because I need water as a reactant. So I'm going to say 2H2O gas breaks down to form 2 hydrogen gas plus oxygen gas. My delta H for this reaction is going to become positive 484 kilojoules. And I'm going to scratch this one out because I've already rewritten it in the form that I needed. Okay, so now I look at it and say, okay, can I cancel things out and add things together to where I can come up with this reaction? So I look at it and I want 2 N2, and I notice I have 1/2 N2. So I can do this as long as and you did this in the assignment today too, as long as you do the same thing all the way through, you're okay. So I want 2 nitrogen, so I'm going to multiply this entire reaction by 4, because 4 times 1/2 is 2. And if I do that there, I also have to multiply this delta H by 4. So let's go ahead and write down what we have. So 4 times 1/2 is going to be 2 N2 plus 4 times 3/2, which is going to be 6 H2. And 4 times 1 is going to be 4 NH3. And that's going to take our delta H to a negative 46 times 4, which is going to be minus 184 kilojoules. I'm done with this reaction. I look at this and I say, okay, 2 water is what I need. I don't have 2. I have 2 and I need 6 in my reaction. So I'm going to go ahead and multiply this whole reaction times 3, which is going to cause me to, oops, it's right there, and this delta H by 3, and rewrite what I have. So 3 times 2 is 6 H2Os. And I'm going to scoot this arrow down here just so that it's really clear what are on the left and what are on the right. 3 times 2 is 6 H2s plus 3 O2s. And my delta H is going to be multiplied by 3, so 484 times 3 is going to be 1,452 kilojoules. All right, so look at this and say, okay, can I come up with this reaction now? So I have 2 N2s, I have 6 H2Os, I have 4 ammonias here on the right-hand side of the equation, and I have 3 oxygen. And in addition to that, I'll go ahead and just write this underneath here like this. In addition to that, I have 6 H2s in gaseous form on the left side and 6 on the right side. And that allows me to cancel those out because they show up on the left and on the right. So now all I do is write down exactly what I have left over, which is 2 N2 plus 6H2O, and that's going to yield 3 O2s and 4 NH3s. And the delta H for this reaction is going to be 1452 plus a negative 184, which is 1268 kilojoules. And this is my final answer. This is what I wanted, because you'll notice that this is identical to what they asked us to find. So our answer is this. It's an exothermic reaction or endothermic reaction. That's the thing you want to look at. And it's a positive, so it's an endothermic reaction. So in order to make this reaction go in this ratio, it's going to require 1,268 kilojoules of heat. Okay, we're going to do one more problem with Hess's Law before you do your problems with your lab partner over this. And this is our answer that we want to come up with right here is the SO2 plus 1/2 O2 yields SO3. And we're going to look at these two reactions and make this reaction out of it. So let's start with looking at our reactants. And SO2 is a reactant. And do we have SO2 as a reactant on the left? No, we don't, but we have it as a product. So let's start first by flipping the first reaction. So we're going to take and do SO2 and flip it to form S plus O2. And our delta H then for this reaction is going to be the reverse, or the opposite. The negative, instead of negative, it's going to be positive 297 kilojoules, meaning that this is an endothermic reaction taking in 297 kilojoules of energy. Okay, so I have SO2 on the left-hand side. Do I have SO3 on the right-hand side? Well, we sure do. So let's go ahead and just put these next to each other and see what happens. See what we have. So we have 2S plus 3O2, and we have 2SO3. And notice on this problem they didn't give us the states, so we're just going to assume that they're all in the same states on both sides. That the SO2 is in, it doesn't really matter what form it is in, but the one we're going to have to look at canceling is the sulfur, and we're going to assume they're in the same state because they didn't tell us any differently. So this one is an exothermic reaction giving off 792 kilojoules of heat. So when we look at this, our SO2 is on the left-hand side, SO3 is on the right-hand side. We don't see, in this reaction right here, we don't see any sulfur by itself. So that means it needs to be able to cancel out. You notice there's 2 here and there's 1 here. So we're going to start by multiplying this whole reaction by 2. So, and rewrite it. So we have 2 SO2 and 2 sulfur, plus 2 O2, and that's going to cause our delta H to be doubled. So we take 297 times 2, which is going to be 594 kilojoules. And we're going to get rid of this one. So we look at it now, and I think we're in pretty good shape. Let's go ahead and see if we can't eliminate what we need to. We want the SO2, and we want the sulfurs to cancel, so let's get rid of those, 2 on each side. Notice that we have 2 O2s over here and 3 O2s over here, so I can cancel 2 of these and leave 1 O2 on the left-hand side. So let's go ahead and write down what we have. We have 2 SO2s, and we have 1 O2, and that's going to go together to yield 2 SO3s. And delta H in this case is going to be 594 plus a negative 792. So it's a negative 198 kilojoules, which just means that there's that much energy given off. Now if you look at it, this is not identical to what they wanted us to have. If you look up here, they want 1 SO2 and a half oxygen. So you notice if I were to take these coefficients and divide them by 2, I would have these coefficients, and that's what I'm going to do. So I divide each one of the coefficients by 2, making the coefficients 1, 1/2, and 1. If I did that to the coefficients, I also have to do this to the delta H, making it 99 kilojoules that's given off when this reaction goes to completion. Now it's time to practice.